Alright, we've learned all about sine, cosine, tangent, and all of the inverses of those three trig functions. Remember, we used the regular trig functions to find the side lengths, and we used the arc trig functions, the inverses, to find angles. Alright, so right now, let's expand on our knowledge of that trigonometry and actually start to use it in real life. Number one, a 6-meter long ladder leans against a building. The ladder makes an angle of 60 degrees with the ground. So first things first, we want to draw a picture. Alright, so we have a ladder right here, and that ladder is 6 meters long. The ladder makes an angle of 60 degrees with the ground. Well, I'll put the ground down here in orange. Alright, and that angle is 60 degrees. Alright, leans against the wall, so I'll draw the wall right here. And let's say this is a building or something like that. Alright, it has windows. Alright, a lot of this is about drawing correct diagrams. Your diagrams don't need to have windows in them, I don't mean that, but they need to be accurate in terms of what's given and what you need to find. Alright, in this question, part A, how far up the wall does the ladder reach? Alright, I'll highlight what that actually is asking. It's asking this highlighted portion, that distance right there. Alright, so in all these trig function problems, what I want you to do is draw a picture and then think about how that picture relates to just pure right triangle trig. Right, we have 6x, and this angle right here is 60. Alright, so this is going to be either sine, cosine, or tangent. Since we're looking for a side length, we're just going to use the regular version of all three of those. And we have an angle, we have the opposite, and we have the hypotenuse. So we're going to use the sine. As I told you, it might be a good idea to write this mnemonic device at the top of every paper, whether it's a quiz, whether it's notes, a test, or an exit slip. So we're going to use the sine of the angle is equal to opposite over hypotenuse. Alright, and then the numbers in the denominator, we simply multiply 6 sine 60 to get our answer. Go to your calculator, make sure that it is in degree mode. 6 sine 60. And that doesn't look like it's right. Oh, I'm not in degree mode. Alright, lesson learned. I got a negative side length. That's always a red flag. There we go. 5.196. 5.196, and we are in meters. So that is the answer to part A. Right there. Alright, part B. How far from the wall is the base of the ladder? I'll highlight that. The base of the ladder is the bottom of the ladder, so we're asked to find that distance right there. So again, let's extract or draw a simpler triangle here, just like we did up above and to the right there. We have 66. We don't want to use this, even though we found it. There's a chance that we're wrong. So if we're trying to find this distance right here, all right, we don't have to use what we just found for that. All right, if you can avoid it, I want you to avoid using an answer to find a new answer. If the first one's wrong, then both of them will be wrong. That's not good. So we have now an angle adjacent a hypotenuse. Adjacent hypotenuse is cosine. So cosine of 60 equals y over 6. 6 cosine 60. Go to your calculator. 6 cosine 60. And we get a nice number 3. So this is 3 meters away from the base of the wall. That is part B. So those are two answers. Number 2. Let's read the question. John leaves school to go home. He drives 10 blocks north and then 42 blocks west. How far is John from the school if one block equals about 450 feet? All right, so first of all, let's put John, he's going to drive north, so let's put him right here. All right, and he is going, well, first of all, he's at school, so it might be helpful to write that down. This is John at school. So from school, he wants to go home, and home is, let's see, we'll go put a dot here. Home is 10 blocks north, 10 blocks, and 42 west. West is this way. So he's going to go all the way over here. That's 42 blocks. And the question, how far is John from the school? This is, of course, John's home. That's where he lives. All right, so this question is, of course, asking that distance right there. All right, we're going to assume that these blocks in this particular city are at right angles. So this is actually not really like a trig question insofar that it's sine, cosine, tangent, but it's really just Pythagorean theorem. Pythagorean theorem. So we'll go 10 squared plus 42 squared equals c squared. All right, and I'll show you a quick shortcut here, how to type this into your calculator all at once. You hit the square root, you hit 10 squared plus 42 squared. So your answer is 43.174. That's what C is equal to. And it's helpful to label that the appropriate label, because the question's not asking us for blocks. It's asking us for a conversion of blocks to feet. Each block equals 450. So all I need to do is figure out if one block equals 450 feet, 43.174 blocks times 450 will give you the answer in feet. So that's 19,428. 19,428.33. Notice we're going to, if I always want to go to the third digit, I examine the fourth digit. That brings us up to a 0 and cranks that up to a 3. So it's 0.33. And that is in feet. That's how far John is away from school. That's how far his home is away from school. And you might see this expression as the crow flies. That means a perfectly straight line. The shortest distance between 2 points is a straight line, and that's, in that scenario, we use the expression as the crow flies. And you know, if you want to get an idea of how many miles that is, all you would do is divide that by 5280, because there are 5,280 feet in a mile. So he lives about just under 4 miles from school as the crow flies. But as you know, you can't, a lot of times can't go diagonally. You know, there are a lot of, some streets go diagonally. In Philadelphia, we have a couple that go diagonally. Moy-Mensing, Passyunk, things like that. But most streets in Philly go north, south, or east and west. All right, so John needs to go on the street, so he has to actually travel quite a bit further. He has to drive quite a bit further than that to get home. If he were a bird, or if he had a helicopter or something, he would have an easier time getting home. Number 3. All right, here we're getting some shadow problems. So suppose a tree that is 51 feet high casts a shadow of 62 feet. All right, so first things first, let's draw our tree. I'm not the best artist here in the world, but we'll get an idea of what this tree looks like. All right, and we'll put a base on it. Let's put a base that is this brown. So the base here, the trunk is brown. All right, that tree has a height of 51 feet. And that casts a shadow that is, all right, so that shadow is 62 feet long. All right, so first things first, we need to draw our little sun. All right, we have a sun over here. Well, that's not very good. Suns usually are drawn like this, All right, so you draw your little sun, right? You want to put some shades on them, go for it, right? And shadows are a result of the sun's rays coming down this way, being blocked by the object and leaving a shadow on the ground in this direction. All right, and that shadow is 62 feet long. And the question, what is the angle of the elevation from the end of the shadow, which is right here, to the top of the tree? So the question's asking you, I'll put it in blue, it's asking you basically what is the angle of elevation. This might be a new idea for you, so it's something that I would probably write down. Angle of elevation is, elevation of course means to go up, so it's going to be this angle right in here. Let's call that theta. Alright, so we're looking at a right triangle situation. We drew our picture. It's a good idea to turn that into a really easy to see right triangle, and we're asked to find theta. Alright, so we have an angle, opposite, adjacent. So we're going to use the tangent of theta is 51 over 62. Alright, since we're looking for an angle, that's a good indicator that we're going to use the inverse tangent, or what we call the arc tangent. So in your calculator now, you hit inverse tangent 51 divided by 62. And that'll give you your degree. It's 39.44 degrees. And that is your answer. Alright, that's the angle of elevation right in here. Number 4. Another tree problem. Let's draw another tree here. Suppose a tree 26 feet in height casts a shadow of length 164. Alright, so this might be a good time to pause the video and give this one a shot on your own. So we want to draw a tree. This tree is a little bit shorter, so I'll draw it down here. Alright, and that is 26 feet tall. 26 feet. That's the abbreviation for feet, just one little apostrophe like that. The angle of elevation from the end of the shadow. Alright, so let's draw a shadow. Again, the sun is over here. The shadow is much longer this time, so that means the sun is a little bit lower in the sky. So that shadow is really long this time. That's 164 feet. And again, it's an angle of elevation problem. So we're trying to find this right in here. Let's call it delta, lowercase delta. So again, transfer that to a really simple to see diagram. And this is the angle we're looking for. It's going to be a tangent again. So we go tangent of delta was 26 over 164, and delta is equal to inverse tangent of that ratio. So we go and hit the right buttons here. Inverse tangent is basically second tangent. And we get just about 9 degrees, a little over 9 degrees, 9.009 degrees. So delta is 9.009 degrees. So that's this little tiny little angle right in there. Number 5. A building is 63 feet high. At a distance away from the building, an observer noticed that the angle of elevation to the top of the building is 41 degrees. How far is the observer from the building? All right, like I said, in the spring, we're going to go on our way over to the Franklin Institute. We're actually going to do projects like this in the city. We're going to take our little clinometers and we're going to measure heights of buildings, trees, statues, and angles and things like that. So it'll be a pretty cool project. So here's our building, right? The building is 63 feet high, and there's an observer over here somewhere, right? And that observer is looking up at the top of the building, and they're noticing that this, I'll draw it dotted, this line of sight provides an angle with the ground. This angle right in here is 41 degrees. All right, that's an angle of elevation. And the question is, how far is the observer away from the building? All right, so we have, that's not a very good picture. We have a right triangle, 63, x, and 41 degrees. So again, tangent, right? Opposite, adjacent. So the tangent of 41 is equal to 63 over x. Now this time the denominator is a variable, so all we're going to do is just pull the old switch trick that I taught you. Move that tangent of 41 down there. So we say 63 divided by tangent of 41. And we get that the observer is 72.473 feet away from, we'll call that distance, away from the building. Number 6 rather. We'll do a couple more. An airplane is flying at a height of 2 miles above the ground. Alright, so let's draw our little airplane here. Let's see, I'm not a very good artist, but we have a general idea of what an airplane looks like. That is flying at a height of 2 miles above the ground. Alright, so this is called an altitude, 2 miles. The distance along the ground from the airplane to the airport is 5 miles. So that is 5 miles. And here's our little airport. Right, here's our airport. And on that airport, let's draw a little radio tower. Right, it's like a radar. Right, the air traffic controllers are sitting up there, and they're directing air traffic. What is the angle of depression? That's a new word. Angle of depression from the airplane to the airport. All right, so here's what I want you to do. I want you to connect the airport to the airplane using a straight line. All right, and the angle of depression is something that is in relation to the horizontal. So if this plane were to keep flying horizontal past the airport, its angle of depression is this angle right in here. So it's the angle between its descent trajectory and the horizontal. All right, we'll call that let's see, I'll just pick like a new Greek letter that we haven't used before, lambda. This is L-A-M-B-D-A. All right, so lambda is our angle of depression. All right, but we know that way back in report period 1, if we have parallel lines, and of course these lines are parallel, if we have parallel lines cut by a transversal in orange, if this thing right here is something we're looking for, well, it's the same as asking for that, right? These were called alternate interior angles. So my point is, if lambda is up here, we can also put lambda down here. All right, these angles are exactly the same. So the angle of depression is this angle right in here, again, between the horizontal and the descent trajectory of the airplane. Be careful not to find this angle. That's not what the question's asking. That's something a little different. That would be the complement of the angle of depression. All right, so let's take that rather confusing looking picture and simplify it. 2, 5, lambda. So we go tangent of lambda is opposite over adjacent. Lambda is inverse tangent 2 over 5. So you go to your calculators and you hit inverse tangent. I'll just type it in as a decimal, 0.4. Remember, 2 over 5 is also equal to 0.4. So you're free to interchange between fractions or decimals. So our answer, our angle of descent, will be 21.801. Now I did some research yesterday, and I found out that the typical angle of descent for commercial airliners is way smaller than that. It's probably, I think it's about 3 or 5 degrees. So this would be an airplane that is basically coming in at a really horrible and horrifying angle of descent. It would be really uncomfortable. And as you know, when you're in airplanes and they descend too quickly, your ears start to hurt because of the pressure. Last one. Support cable runs from the top of the telephone pole to a point on the ground 42.7 feet from its base. So let's draw ourselves a telephone pole in brown here. So we've got ourselves a telephone pole. All right, a cable runs down. A cable is in gray. And that cable makes an angle of 29.6 degrees with the ground. All right, and that cable runs all the way over here, right? And that angle that it makes with the ground, I'll extend that a little bit, that angle that it makes with the ground is 29.6 degrees. All right, find the height of the pole and the length of the cable. All right, so we have more information here, 42.7. That is the distance that the telephone pole is from the end of the cable. All right, so we're looking for, number one, this distance right here. We'll call that h rather. So we go tangent of the angle is h over 42.7. All right, so let's find that. We'll multiply 42.7 times the tangent of 29.6. So the height of the telephone pole is 24.257. 24.257 feet is the height of the pole. Next question, what is the length of the cable right there? That's question number 2. So that is this question right here. We'll call that C for cable. All right, so that's a question where we want to maybe simplify the picture again. As a general rule, it's probably a bad idea to use that new h that we found, just in case it's wrong. It's also approximated. Even though we brought it out to 3 digits, it's not exact. So let's use our given information that is exact. And I'm looking at an angle, adjacent, and hypotenuse. That's a cosine problem. All right, cosine of an angle is equal to adjacent over hypotenuse. So denominator is your variable, so just pull the old switcheroo there, and you go 42.7 divided by cosine 29.6. And the length of the cable is just about 49 feet. We'll call it 49.109. Alright, and that is your length of the cable. Notice the cable is the longest side in this right triangle. Right, the telephone pole is about 24 feet. This is about 49 feet, and the distance from the bottom of the telephone pole to the end of the cable is about 43 feet. Alright, so there's 7 examples there on word problems that have to do with trig.